All right, hello everyone. In this tutorial, we'll be going over how to use Pi Spline for XAS analysis. So to begin, I typically will load my data into Athena. This way I can do any preliminary normalization on it if the data is clean, as well as calibrate my data set. And those are important steps to take care of, I think, before using Pi Spline. So in this case, I've got a data set here. You can tell it's pretty clean. Energy space looks good. K-space, the data look good. It's a little odd that, the XAFS are oscillating so much out here past a K of 10. I happen to know that I have a very heavy backscattering atom in this sample, so likely that's what this is from. But we're going to spline it to see what we can see. So to begin, once I've calibrated my data and I've normalized it and everything, what I'm going to do is come here and check the box next to the data that I want to use. Then I will go File, and I'm going to save my current group as normalized energy. I'll go ahead and save that here. Pyspline is a little finicky, so you need to make sure it's a .dat file, not a .nor. So I'll save it. Next, I'm going to open up that file in Excel. Let's go find it. And, oh man, there we are. There we go. All right, delimited. And there we are. So this is the normalized data file from Athena. You can see all the normalization parameters are here, but we don't need that. And in fact, we can't have it for Pyspline, so I will delete it. The columns that this prints, the 4 that are relevant are here, but actually only 2 of these are relevant. There's the energy, your normalized data, the background, your flattened data, and your flattened background. We just care about these 2. So I'm going to go ahead and delete all the other columns. We just need a flattened normalized data. And actually for Pyspline, we can't even have column headers. So I'm going to go ahead and delete the column headers and save again. Next, we need a value of E0. So remember, E0 is basically where your XAFS begins. Common way of detailing that is the maxima of the first derivative, maximum of the first derivative. So here it looks like we're actually a little off. So that's not a problem. We'll get the value. I'm going to pluck it from my graph. There we are. And that looks fine. So I'm going to copy that. And now let's launch Pyspline. So launch Pyspline by double-clicking the executable in the file. Within the file, don't move it. I think it'll break if you take it out. And you're greeted with 4 windows. So to bring our data into Pyspline, we're going to go File, Import Raw Data. I'm going to go find the .dat file that I just saved, and it's this one. You'll be greeted with a window like this. You've got some choices for elements, but you'll notice in this case, I'm using iridium. Iridium's not on this list. That's not a problem though. I'm going to leave K-edge the same. I also don't think that matters. What I'm going to do is custom energy value, and then I'm going to paste that value of E0 in here and hit OK. And that will bring my data in. So you will see that we're greeted with four windows with our data. And I usually will arrange them something like that. The first of these is the background subtraction. So you can actually do normalization here also. But unlike Athena, which allows you to do a post edge and pre-edge, here you get the option of either a post edge or a pre-edge line. So in my case, I've already done this in Athena. So I basically just want to get this line to be flat because I'm not trying to subtract any more background. So that looks okay. I'll minimize that. Next, we'll want to start our splining. So to do that, we do it here. You have a couple options here. You can specify the number of knots. So it's pretty common to do a 3-segment spline, so that's 4 knots. And it's here you can see the segments are 1, 2, and 3. The order of our segments, this is the polynomial order. So in the first segment, it's a second order polynomial, which is here. And you can kind of see that. You can see this parabola looking thing kind of coming off. And then in the second and third segments here, it's a third order polynomial. Now, if you've got data that's like to a higher K, here my data is only like K of 13. But if you have higher quality data or that goes further out in K, you can add more segments. Don't add too many. I've splined K of 18 data before, and I think I was able to do it with 4 segments, maybe 5. But you definitely want to use as few segments as possible. You also want to basically keep the polynomial order to 2 followed by however many 3s you have. When you start increasing the polynomial order, you're increasing the chance that your polynomial will start canceling out the oscillations in your XAFS. Pardon me. So now I'm going to go ahead and spline this data with a 3-segment spline, 4 knots. And I'm going to do it the same way that Athena tries to do it with its RBKG. So I'm going to try to minimize these low R components while also trying to maximize the intensity of the first shell and ideally the second shell as well. And then also you want to try to get this this line that comes out of your post edge and through your pre-edge region. You kind of want to get this as flat as possible as well. So you'll see that the default values for your spline knots, so these lines specify where the knots are in your spline. You'll notice that they were basically evenly spaced in K space. So we still want our end result to be more or less evenly spaced in K space. But of course, we'll have to move them around. We don't want to end up in a situation where we're something like this with 2 of our knots very close together. So to begin, actually I already kind of like this. See if I can. So this is the game then. So you kind of want to play around with your different levers, trying to minimize. In this case, I'm trying to minimize this feature because I know this is iridium. Iridium's not going to have something at like 1.4 or 1.6 angstroms, probably not at the oxidation state that this is at anyway. There's iridium 3, or it should be iridium 3. So you can already tell it's, I'm already pretty close. Another thing you can do, it could be, say I had a lot of noise at the end of my spectrum, at the end of my XAFS spectrum, you can refine your Fourier transform window. That's these blue lines here. So you can see as I move my Fourier transform window to something like this, that's probably like this is at about 2.7. So in reality, I would probably, set it somewhere around 2.5-ish, maybe 2.7. You can kind of follow to see where it makes sense for your data. Then you should have one at this end too. So if you had a lot of noise out at high K, you could exclude that from your splining. But in this case, I'm happy with that. And then because I moved my Fourier window in, I can probably also move this in a bit, this first knot. Actually, that looks fine. All right. So this is already starting to look okay. And I'm never going to minimize these completely, I don't think. I can try adding another knot and seeing what that does. But I don't think this is going to be the answer. Yeah, no, I'm pretty unhappy with that extra segment. So we'll go back to this. Let's see if I bring this back out. Doesn't really do a whole lot. Yeah, that's not really doing much. Yeah, so this is probably going to be about as close as I'm going to be able to get this. So you can see now with this final switch, you can kind of watch the intensity of these 2 peaks here. And I am trying to kind of maximize the intensity while minimizing those low R components. I think that's probably as close as I will get here. Yeah, I think I'm happy with this. Okay, so we'll call this good for now. We have our first shell here, and then a split second shell. Yeah, if I were doing this for real, I'd probably spend another 5 minutes or so trying to see if there's any other way I can minimize that, but I've already done this for this sample, and I think this is about as clean as it gets, so. Yeah. Okay. All right. Yeah, well, we'll call this good. Okay, so next, once you're satisfied with your splining job, we'll go and we'll come back to this screen, and we'll go File, Save As. We'll name it something, and there we are. And then you can just close out. So what I did is, when you save a Pi Spline, it saves as a .d file. So that's actually this one. I don't know why it dropped the file extension. So it's a .d file. So that means you can actually, if you wanted to, you can just reopen that .d file directly into Pi Spline. And it will populate with all of your normalization and splining parameters already in there. So next, we need to do one thing before we can bring this into Athena to compare it to our other data set. And that is, we have to adjust it from a K3 weighting to a K1 weighting. So Athena, when you import data into Athena, Athena will try to cube whatever chi of k data you bring in, at least as far as I understand it. So we need to make the data from Pi Spline back to K1 weighting. All right, so to do that, I'm going to go and bring in the data. Here it is, the .d file. That's delimited. I always forget if it's space or comma. And here we are. So a bunch of columns. We have energy, our K space. This is our K spacing. Background, so our spline. So this was our pre-edge feature, which I'm sorry, the line that we first did. So this should be basically flat. This is the normalized data, which should again just match up with the flattened data that we imported. This is our spline, and then this is the XAFS, and these are the spline parameters. So this is actually K3 data. So what we need to do is turn it into K1. So to do that, we take the XAFS intensity and we divide it by the K position cubed. Usually do this as an if statement. And then take the XAFS, the K cubed, and divide it by the K position cubed. There we are. Okay, and that should be it. So let's do two things. We'll autofill. Let's snag these two columns. Let's put them in a new sheet. Delete this. The file, I'm going to save this as an Excel sheet. I don't want to save over my .d file, or I won't be able to open it in Pyspline again if I need to adjust things. You can see that this is now K1 weighted. If I insert it as a scatter plot, that's K1 data. Next, I'll just grab it again. I'm going to put it into another new sheet. And this time I'm going to save it as a CSV file. So there we are. We'll just go call it the same thing. And there we go. So I'm going to close these, don't save. And now we'll import it into Athena and see what difference we made. So go import IRB, the CSV file we just did. Because we're importing chi of k data, we have to specify that. So from this drop-down data type, select chi of k. And then we have our K space as the radio dial here. And then we'll select the second box as our K K data. So you can see Athena's gone ahead and applied a K cubed weighting to it. So there we go. And there we are. So this is what the data that we've splined looks like. Let's go ahead and compare it to what Athena would have done. So to do that first, let's specify the same Fourier transform range and windows for these. So from the K-space, you can see there's a slight difference. I've maximized some intensities. I've reduced some intensities. Importantly, here at the end, I've kind of tied the end of my data set down a little bit, although this is outside of the Fourier transform range that I'll be testing. So let's go ahead and take a look at that. So here with this data, you can see I've reduced some of the intensity here out at low R. I've maximized my first shell intensity while basically not affecting really, it looks like the second shell. And then the rest of the spectra, or the Fourier transform, sorry, looks basically the same. So I'm satisfied with this. So this then right here, this is what I would bring into Artemis to do my shell by shell fitting for XAFS. Okay, so for the second part of this, let's take a look at a slightly messier spectra and see what we can do for normalization. So in this case, this data set is kind of noisy, right? It's got some noise in the pre-edge and some noise in the post-edge, and it kind of curls up at the end like that in a kind of a funny way that tells me that there's probably iron in the sample. This is manganese, and I think this is from a soil, so this is actually likely the beginning of the pre-edge for the iron edge, so we should actually just truncate that off. I'll do that really quick. Let's truncate it right here. It looks okay, 7030. Just truncate that. There we go. All right, so same protocol. I'm going to check the box. And actually what I can do is I can also deglitch that pre-edge region. That might make the normalization a bit nicer. Let's see, is there anything else? Yeah, I'll deglitch a little more here. That's really hard to see. Let me maybe just grab like one more point. I lied, let me grab one more point. Okay, so save this. So let's go ahead and now save this again as this time U of E. I don't want to save the normalized because I'm going to try to normalize it in Pyspline. So we'll save it as mu of E. And yeah, this looks fine. Again, instead of .xmu, we'll do .dat. And I don't need the E naught value because it doesn't really matter for just normalizing the XANES. Okay, so now import raw data. We'll go find the spectra. The spectrum is right here, I think. In this case, oh, something didn't like that. Maybe I hit a wrong button. Yeah, it doesn't. Okay, let's take a look, see what's going on. So this, this looks. Oh, I'm sorry. You know what? Yeah, I'm getting ahead of myself. Sorry, we've got to do the normalization thing in Excel. So let me just open this up really quick. It'll be the same protocol, just about. It's the wrong thing. Sorry. There we go. Browse. Let me just pick it out really quickly here. All right. Yep, that looks better. Okay, same protocol. Delete all of this nonsense up here. This time we care about the unnormalized data. So the two columns that we're going to keep are the mu of E here and the energy. And again, delete the column headers and save as a .dat. Okay, now this should go more smoothly. Here we are. So this time I'm just going to use probably the default value for manganese because I'm not doing any XAFS splining here. So it doesn't matter what that is. Okay, so because I'm not doing that, I'm just going to minimize those windows. And I'm going to maximize this. So we only get one line here. So I'm going to try maybe two different things. The first one I think will be the easier, which will be to, and I'm sorry, I should have kept this one up. So this will tell us how good of a normalization we're doing. So you can see the post edge region kind of slopes up like this. So I can match this with just kind of a straight line. Actually, can I? Yeah, so I can reduce the order of my background. So right now it's a line, now it's a parabola or a second order polynomial. Now it's a cubic polynomial. We could stick with the line, and you can see from this, a line actually does a pretty good job. Typically when I'm doing this, I'm keeping an eye on a couple of things. One is the post edge oscillations here to make sure that I'm basically bisecting those oscillations with the one line. And then two, I watch the edge of my spectra to make sure I'm not dipping up or down at the end. So even though this looks linear and this is a line, I'm kind of seeing that the end of my spectra looks like it's a little bit below the one. So I'm going to just change this back to that. So to a parabola. So this looks fine. So in all honesty, if I was splining this for XAFS, or if I was normalizing this for XAFS, this is what I would do. And then I would go ahead and probably do the splining here. But say you're interested in XANES analysis and you're interested in like quantizing some like pre-edge feature. Well, in that case, you've got to make sure. So even though this is a good normalization, you can see how the pre-edge region is still suffering from this elastic scattering peak. So to do that, I'm going to move my my two control units here down to the end. You can see that looks very bad. So I'm going to play around with this a little bit to try to see what I can do for this edge jump area. Okay. Yeah, this is very tenuous. So you can see this is, and this is pretty noisy. Yeah. I don't think that's going to help. Okay. Well, I was hoping to have an example where I could show you how to get a general slope like that, but that you might have to do that in 6-pack. I think will allow you to fit a Gaussian or something like that as your pre-edge to get rid of this peak. So you could try that in 6-pack. For my purposes, this is probably also fine for XANES. So again, for XANES, just like for XAFS, you want to watch that this region up here kind of oscillates around mu of equals 1. For XANES, you want to make sure that your pre-edge region is right down around 0. And so I really don't like how part of my pre-edge region is significantly above 0 right here. And that's a critical region if I were going to do any fitting of like a pre-edge feature or something like that. So let's see what we can do there. Okay, so this looks pretty bad, but let's see what we can do. So you can see now, now we're flat here. So now we are hugging 0 with our pre-edge region, but our post-edge region is still sloping up. This may not be fixable. That's pretty close. Okay, so this is pretty close. So this, I might consider this for XANES analysis. So critically, if I was fitting a pre-edge feature, now my pre-edge region is hugging 0, and my post-edge region doesn't deviate from 1 until, much further than the XANES region. So this could be okay. All right, that's probably a little better. So now we're almost hugging 1 for the whole time, or deviating right at the very end. But we're doing a better job of hugging 0 at the pre-edge. So if you're doing XANES analysis, this would probably be a better bet to do for your XANES analysis. Yeah. Okay, let's try this. Yeah, see, I can't go to a higher order polynomial because it just does that. So you're gonna have to keep it aligned for this one. Okay, well, let's call this about good. Let me see if I can get it back to where it was before. That's very important. There we are. And there we go. Okay. Okay. So that's close enough, I think. So then you just follow the same protocol of saving this as a .d file. So save it, and then you can actually, I believe, just directly, possibly directly import this into Athena, if I remember correctly. You just have to select the correct columns. So energy is column 1. Then you'd want the normalized, which is going to be number 6, I think. Yep, there you go. And that's your normalized data. And then you can compare this. Sorry, I think it was S5. I mislabeled this. There we go. And now if we lay them on top of each other, you can see they're pretty similar. You know, my spline is a little above that, so you can kind of see with this really noisy pre-edge feature here. This might give you a slightly better chance of fitting that, maybe not. I think with data like this, you'd have to probably play around with both and see. Yeah, it's kind of funky, isn't it, how this kind of dips here. This is very noisy data. This data I don't think would be suitable for pre-edge analysis. So in light of that, you'd probably be better sticking to the foregoing the XANES analysis of any kind of pre-edge, and instead just trying to do this post-edge line, fitting it like that, and then moving on with your XAFS, and that's probably what would be the best thing to do. So with that, I hope that's a useful tutorial for you all on how to use Pi Spline for data normalization and XAFS Chi-F-K extraction. And so with that, thank you for your time, and good luck.